here today, Farhangi will talk about the Ergodic Hierarchy of Mixing, Będlewo theorem, and the Ergodic theorem of noncommuting.
So firstly, I would like to thank the organizers for giving me the opportunity to speak today. And I'll begin by showing you all the plan for the talk. I guess I should be. There we go. So firstly, I want to review some basic stuff, namely just what is van der Corput's difference theorem, how do we use it in ergodic theory, and the ergodic hierarchy of mixing. And hopefully this will be review for this particular audience, but if I do it correctly, then the abstract nonsense of section 2 will actually be down to earth and sensical. And then even if I succeed in doing that, you may still want some applications. So that's what will come next. I'm going to show you 4 applications to multiple ergodic averages that involve non-commuting operators. And most likely we won't have time to get to section 4, but since I replaced the assumption of commutativity with the assumption of singular spectrum, I do have examples of systems with singular spectrum, just in case there's some extra time at the end. That being said, let's go ahead and get into it. What is van der Corput's difference theorem and where do we use it? So it first came up in the context of uniform distribution, which is something we should be very familiar with because we've already been talking about it on nil manifolds and not just the 0-1 interval. In particular, van der Corput said that if we take a sequence in the 0-1 interval and all of the differences are uniformly distributed, then we can conclude that the original sequence itself is uniformly distributed. And this is useful because it lets us reduce complexity. So for example, if we take an irrational alpha and we want to show that n squared alpha is uniformly distributed, we can take the differences become linear, which we can directly show to be uniformly distributed. And then we conclude that n squared alpha is uniformly distributed. And of course, by induction, we can show that polynomials times alpha are uniformly distributed. Now, when we're dealing with ergodic theory and multiple ergodic averages, we usually work in Hilbert spaces, namely L2 of our measure preserving system. So we have a few other forms of van der Corput's difference theorem that show up. The one that most closely resembles what I just showed you in the context of uniform distribution is what we're looking at right now. So we take a Hilbert space and a bounded sequence of vectors xn, and we assume that all of these Shazaro averages are equal to 0. So the inner product here is the analog of the difference that we had before. And this is how we're reducing complexity. So if all of these Shazaro averages are 0 of the inner products, then we conclude that the original sequence of vectors will converge to 0 in norm. Or I should say the Shazaro average of the original sequence of vectors will converge to 0. And then when you look at the proof of this theorem, which is relatively short, you just use some Cauchy-Schwarz, you realize that you can actually weaken the assumption. So one of the weakenings is that we don't actually need each of these Shazaro averages to be 0. We just need that the Shazaro averages tend to 0 as the difference h goes to infinity. And then we can get the same conclusion. And again, when you keep looking at the proof, you realize that you can weaken the assumption even more. We don't need that these averages tend to 0. We just need that the average of the averages goes to 0, and we get the same conclusion. And of course, one question that I was wondering about is, what's the point of these first 2 van der Corputs if we can just always use the third one, because it has the weakest assumptions and it still gives us the same conclusion that the other 2 had given us. And another thing that I was wondering is, why do we have 3 van der Corput difference theorems in Hilbert spaces, but only one of them in the context of uniform distribution? Well, I don't have time to answer the second question for you in this talk, but I believe that I should at least be able to answer the first question by the time we get to section 2. Okay. So now, where do we use van der Corput's difference theorem? Well, we first start with a classical theorem of Poincaré. which is just a simple consequence of the pigeonhole principle. So we don't need any van der Corpeting to get this result, where whenever we take a set of positive measure, we can say that the set eventually returns to itself at some time in the future. Now, if we want to make this result slightly more sophisticated and get this classical result of Furstenberg and Sarkozy, where we've refined Poincaré's recurrence theorem because now the time that we're returning is a perfect square. This result, I argue, does use van der Corput's difference theorem. If you look at Furstenberg's proof, then he uses the uniform distribution of n squared alpha. So that's one of the reasons why I would argue it uses van der Corput, because I think the easiest way to show that this is uniformly distributed is through van der Corput. Or if you look at a survey of Bergelsen, then there's an alternative proof of this that directly uses the Hilbertian van der Corput that I had a few slides ago. Yes, so this is also in Furstenberg's book, which will be referenced on one of the future slides. So another direction in which we can generalize Poincaré's recurrence theorem is the Furstenberg multiple recurrence theorem, where rather than only looking at A intersected with t to the minus n of A, we take a multiple intersection. So now we're intersecting L plus 1 terms and requiring that the multiple intersection have positive measure. And while I was unable to find any hints of van der Corput in Furstenberg's original proof, if you look at the proof presented in Einsiedler and Ward's ergodic theory with a view towards number theory, they directly use the third van der Corput that I listed. Or if you look at Furstenberg's book, where he technically proves something more general, because he proves it for commuting operators, not just powers of the same operator, he has a lemma which I claim is morally equivalent to what I listed before, even though it's not exactly the same. And then, of course, I've listed here a special case of the polynomial similarity theorem of Bergelsen and Leibman, where now, rather than just looking at TNA and T2NA, we have commuting operators, T1, T2, up to TL. And these powers, rather than just being n and 2n and ln, we pick polynomials, P1 of n, P2 of n, up to PL of n. And we can make this multiple intersection have positive measure. And they have a lemma in their paper, which is very similar to this third van der Corput that I've listed, but it's a little bit different since they're working with commuting operators, but I believe it's of the same spirit. So in general, what I'm trying to say here is van der Corput's difference theorem and its variations are a useful tool for reducing complexity when we're studying multiple ergodic averages, which is something that we care about when we study recurrence. Now, to explain or to make sense of the generalizations of van der Corput's difference theorem that I'm going to show you later on, it'll be helpful to just quickly recall the ergodic hierarchy of mixing. And I've listed a particular form of it here, which is going to be most useful for my purposes. So this will appear, for example, as a theorem in Walter's book, that you can take the standard definition of the ergodic hierarchy of mixing from measurable sets and convert it into some functional definition like what I've listed here. And the gist of it is that if you look at these, if you look at L2 of your measure space and you normalize the function so that they have zero integral, which is why I put a 0 over here, then we can start looking at inner products of this Koopman operator ut of n applied to f with g. And the rate at which these inner products decays to zero is going to tell us the rate of mixing of the underlying measure preserving transformation. So if a Shazaro average of these inner products goes to zero, the system is ergodic. If a strong Shazaro average of these inner products goes to zero, the system is weakly mixing. If the inner products just directly go to zero in the limit, then we have strong mixing. And if this L20 has an orthogonal basis of the form UTN FM, then it has Lebesgue spectrum. And I think this is maybe the definition that appears most often when I hear Lebesgue spectrum. But just to make it seem more similar to what I had with 1, 2, and 3, I've listed this equivalent definition, which is also going to be helpful for the next slide. So rather than this orthogonal basis definition, we can say that for any F and G, if we look at this sequence of inner products, this countable sequence, then it'll be the Fourier coefficients of some L1 function. In particular, this is with respect to Lebesgue measure here. And we can see now that this condition 5, this Lebesgue spectrum, is stronger than condition 3 because the Riemann-Lebesgue lemma tells us that these Fourier coefficients are going to go to zero. Now, the reason I've mentioned this definition specifically in this form is so that I can state this theorem, which also appears in Walters. So this is almost the same as the definition I had on the last slide. The only difference is that everything is symmetric now. So rather than taking a F and a G in my L20, I'm just taking a single function F. And now if I want to check if my system is ergodic, I don't need to check that these inner products go to zero for every F and G. I can just check for every F and F. So that's a lot less to check. And similarly for weak mixing, I don't need to check for every F and G. I can just check for every F and F. So if these averages go to zero for F and F, then the averages will also go to zero for F and G. That's the content of the theorem. So of course, the same thing happens for strong mixing. And then this is why I was giving the alternative definition of Lebesgue spectrum, because the definition 5 is easier to make symmetric, as I've done here, where rather than looking at the sequence of inner products of F and G, we look at the sequence of inner products of F with itself. And now what changed is that the function H is a non-negative real valued function, as opposed to just some complex valued function. So the point is, if we just check correlations of a function with itself, then it can tell us about correlations of the function with other functions, which is what we had in the original definition of ergodicity, weak mixing, strong mixing, and Lebesgue spectrum. Yes, I should have mentioned that. Thank you. So the other thing I skipped on the last slide is that this definition of the system being ergodic, I can also, rather than saying that the entire system is ergodic, I can take an individual function f and say that the function f is ergodic. So namely, if there's a single f such that these averages go to zero for every g, then that f is going to be ergodic. And such a f could exist even if the system as a whole is not ergodic. So that's what I was saying here when I said that the definitions apply to individual elements as well. So now, this theorem, I guess I'm trying to be sneaky and hide or state two theorems in one. So if this is satisfied for every possible f, then the system is ergodic. But if this is satisfied for a single f, then that element f is ergodic. And then same thing here, right? If it holds for all f, then the system is weak mixing. But if it holds for a single f, then that element f is weak mixing. So that's what I mean when I say that the theorem also applies to individual elements. Does that clarify the situation? Yes, yes. So now we'll see if I did a good job in section 1. Namely, if you understand section 2 before I get to the applications, then I will have succeeded. So one of the generalizations of van der Corput is the following. We take our bounded sequence of vectors in the Hilbert space, satisfying this condition, which is exactly the same as what I showed you earlier, that we look at these Shazaro averages and we say that the average of the Shazaro averages goes to 0. And now, so under this assumption, which is the same as the previous assumption I had for the third Hilbertian van der Corput, the conclusion is stronger than it was before. The sequence xn is a nearly weakly mixing sequence. And what does that mean? Well, it'll be easier for me to wave my hands a little bit and give you a almost definition than the precise definition. But don't worry, when I give you applications, they will be precise applications and not almost applications. So that's where I'll deliver the precision. In some sense, you could be correct. So what this means is if we take any other bounded sequence yn in the Hilbert space, and we look at these Shazaro averages, which are imitating an inner product, right? The Shazaro average of inner products is like an inner product between the sequence xn, or in this case, the shifted sequence xn plus h, with the sequence yn. So this inner product of sequences will go to 0 in average. And that's what we had in weak mixing, right? Weak mixing just said that the strong Shazaro average of some inner products is 0. And now all I'm saying is that the inner products is inner products between two sequences. So in particular, this does imply that the xn's average out to 0, and that you could even take some weighted averages that will be 0. But I'll list the weighted averages on the next slide because that's going to be more relevant for our applications. The only other abstract nonsense I want to mention, just in case there's anyone here who likes ultra products, is you can interpret this as taking a ultra power script H of the original Hilbert space H. And then in this ultra power, you have a unitary operator, which is induced by the left shift. And it is actually unitary, despite the fact that you're losing an element. And with respect to this unitary operator, your sequence, which has now turned into a vector in the ultra power, is going to be weakly mixing. But if you don't like ultra powers and whatnot, you don't need to worry about that, and you can safely forget about that comment. Now, this is maybe the more important generalization of van der Corput's difference theorem, because this is what we're going to use to get our applications for non-commuting ergodic averages. Now, again, we start with a bounded sequence of vectors in the Hilbert space. And now I'm saying that we look at these Shazaro averages of inner products. And if they are square summable, then the sequence is spectrally Lebesgue. And you know, maybe we don't really need this full square summability condition. The only important thing is that this is obviously satisfied if each of the Shazaro averages are 0, right? So this includes the very first Hilbertian van der Corput that I showed you. And then if you want, you can find some other sequences where the averages aren't 0, but they're square summable, and you can still use this. Now, what does spectrally Lebesgue mean? Well, let's say that our Hilbert space is L2 of a measure space, because that's usually the Hilbert space we like when we study multiple ergodic averages. And now we take another bounded sequence that's spectrally singular. And I haven't defined this, but basically, as we're going to see in the future slides, if Yn is generated by a measure preserving system that has singular spectrum, then Yn will be spectrally singular. So it's very easy to generate these sequences Yn, even though I haven't given you a precise definition. But for any such sequence, this Shazaro average will converge to 0 in norm. Right? So the original van der Corput was just telling us that the xn's would have a Shazaro average of 0, but now I'm saying I could take a weighted average of xn times yn, and it's still gonna go to 0. And this is gonna be the main ingredient for the 4 ergodic theorems with non-commuting operators that we're gonna see in the next section. So these are both bounded sequence. Maybe I didn't say that Yn is bounded here, but that's a good point. I should have written that Yn is also bounded, and then you don't have to worry about that. Thank you for pointing that out. That's why I assumed the Hilbert space is now L2, so that we can multiply our bounded functions together. But if we were working in just an abstract Hilbert space where multiplication may not be defined, you can just let Yn be complex numbers. You can take some sequence of complex numbers generated by some system with singular spectrum, and then that weighted average is going to be 0. Correct. Because H is now L2, these will be a bounded sequence of functions. Yes. No, I see your point. Yes, it's in L infinity. Yes. So I should have prepared that better, but Yn is in L infinity, so they are pointwise bounded. Okay. So one comment I think worth making is that to upgrade from weak convergence to strong convergence, which is what we have here, it does necessitate a new proof of van der Corput's difference theorem. And then, I've mentioned 2 of the van der Corputs corresponding to the ergodic hierarchy of mixing here. I mentioned weak mixing and Lebesgue spectrum, but the analogous theorems for ergodicity and strong mixing and mild mixing also exist. So I've written those out, and there's also similar theorems in the context of uniform distribution. You can get a ergodic weak mixing, strong mixing, mild mixing, and Lebesgue spectrum van der Corput for sequences in the 0-1 interval. But I don't have time to discuss those in this presentation, but I'd be happy to talk to you about them afterwards if you wanted to. So now, while I hope you enjoyed those abstract theorems, of course, they'll always be better if there's applications. So that's what we have next. And I want to show you 2 background results just to give some context for these applications before I get into the applications themselves. So firstly, I just want to give an example to remind everyone how badly ergodic theorems can fail if we make no commutativity assumptions. So Furstenberg in his book had already written about some examples about ergodic theorems failing when you don't have commutativity, and then Behrend had also another example, and Bergelsen and Leibman showed that in solvable groups you can always cook up such a bad example. And here I've just picked example of Frantsikinakis, Lacine, and Weirdle. So in this particular example, we say that we take any injective sequences A and B from the natural numbers into Z that we want, or Z without 0. And now we take any set F, any subset of the natural numbers, and we can create a probability space and 2 measure preserving automorphisms, T and S, where we're not making any commutativity assumptions between them, but conveniently, both of them will be Bernoulli. And then we can also pick a set in this measure preserving system such that when we look at the intersection, so the measure of t to the minus an of capital A intersected with s to the negative bn of capital A, this intersection will be 0 exactly when we want it to, because it's exactly when n is in our predetermined set F, and then it'll just be 1/4 when we want, namely when n is not in F. So we can, regardless of what sequence A and B we choose, we can control precisely when this average is 0 and 1/4, and we can make it oscillate or behave however badly we want it to behave. So I think this is a nice example to show that there really is no hope of having an ergodic theorem if you just make no assumptions at all on your transformations. And it's a good justification for why much of the previous literature involved commuting transformations and nilpotent transformations. And then, as I mentioned already, we know that solvable transformations is where we start to have problems. So what can we do if we don't want to make a commutativity assumption? Well, we have this theorem of Farhangi, where he replaces the commutativity assumption with a 0 entropy assumption. So here we're going to take some Hardy field function. And if you haven't seen that before, you can just think about a of t equals t to the 1.5. That's a simple example that will work. And basically, we assume that this Hardy field function is not too close to a polynomial, which is what this limit condition is telling us. And now we take a probability space and we take two measure preserving transformations, where again, I should emphasize that we have made no commutativity assumptions between t and s. But in place of commutativity, we assume that the system, when we use the transformation t, has 0 entropy. And as I mentioned before, we do need some assumption, and we know that 0 entropy is arguably the antithesis of Bernoulli, which is what we had in the previous example. So it seems like a reasonable assumption to put in this case. Now, the first part of this theorem says that if we take two L infinity functions and we look at these ergodic averages, T and F times S to the floor value of A and G, then the Shizaro average will converge to what we expect, namely the expected value of the first function F onto the invariant sigma algebra with respect to the transformation T, because we have a T and F together, times the expectation of the second function G with respect to the invariant sigma algebra of S, because we have S and G together. And the convergence is in norm. And then as a consequence of part one, we can derive a application in recurrence. Namely, if we take a measurable set in our probability space, and we look at these intersections, the measure of A intersected with T to the minus NA, intersected with S to the negative floor value of AN of capital A, then the Shizaro average is going to be at least measure of A cubed, which is as good as we can hope for it to be. So we can actually have some quite nice ergodic theorems in this non-commutative situation. And you may have noticed back here, I pointed out that this assumption keeps the sequence A to be far away from polynomials, right? If A of t equals t to the d, then we're not going to satisfy this limit condition. So it's a natural question to ask if you can do the same thing for polynomials. And in this paper, Farhangi asked this question, and later on, with the help of host, he answered the question in the affirmative. The small catch is that because polynomials have some divisibility problems, if you want to have the ergodic averages converge to the correct value rather than just having the limits exist, you will need to make some sort of a total ergodicity assumption, but that's to be expected. And then, and another thing to mention is that in this polynomial situation, we do assume that the polynomials have degree at least 2. So last I checked, it was still open what happens if you take a linear polynomial and you keep the 0 entropy assumption. And then another thing I should mention about 0 entropy is that 0 entropy is strictly stronger than singular spectrum. So if you have a system or a transformation that has singular spectrum, it will also have 0 entropy. And these notions are different because the horocycle flow is a natural example of a system that has 0 entropy and Lebesgue spectrum. So now I'm finally ready to tell you the first of my applications, which is related to this theorem of Frantziki-Nakis as well as Frantziki-Nakis and host. So I have almost the same setup. I start with a probability space, and we take 2 measure preserving automorphisms, and now I assume that my T has singular spectrum rather than 0 entropy. So this part is less general. And then for my sequence of powers, rather than assuming a Hardy field function or a polynomial, I'm taking a sequence of integers, and I am assuming that this different sequence, kn plus h minus kn times alpha, is uniformly distributed in the orbit closure of alpha for every real alpha and integer h. So obviously, if alpha is irrational, then this just means I want the sequence to be uniformly distributed in the 0-1 interval. If alpha is rational, then the orbit is finite, and I just want it to be uniformly distributed within the finite orbit. So, and these conditions are satisfied by the Hardy field functions that we saw on the previous 2 slides. So I can assume that Kn is one of those Hardy field functions. For example, I can assume that Kn is the floor value of n to the 1.5. Now, the first part of this is that for any bounded L infinity functions, if we look at these ergodic averages, so it's the same as what we saw before, right? These ergodic averages converge to the expected value, which is the product of the expected values. All I've done is replace floor value of an with kn, the sequence that I mentioned above. And the way to prove this is that this assumption on uniform distribution is exactly the assumption that I need so that I can take this sequence of vectors, the sequence being skng, I can apply van der Corput to this sequence of vectors and deduce that this sequence is spectrally Lebesgue. And then essentially by definition, this other sequence, TNF, is spectrally singular because it's generated by a system that has singular spectrum. So by the generalized van der Corput, if I take an average of this spectrally Lebesgue sequence weighted with some spectrally singular weights, the average is going to be 0. So the only thing that remains is going to be the constant portions, namely the expectations onto the invariant sigma algebra. So after you prove the generalized van der Corput, proving this theorem is basically 1 page, or, you know, I can confidently say that the proof is 1 page, but if you put the statement on there, it's going to be slightly more than a page. And then, of course, we can play the same game as before, that once we have convergence for the L2 of the functions f and g, we can derive a corollary for just measurable sets and recurrence. So this should not be too surprising. And then the other thing we want to do is say something about polynomial sequences. What do we do if kn is n squared? Because even though n squared will satisfy this condition when alpha is irrational, n squared will not satisfy this condition if alpha is rational. For example, if alpha is 1/3, we're going to have some problems. So what we do is we just throw away all of the rational alphas by assuming that the system S is totally ergodic. And then when we do that, we only need uniform distribution for the irrational alphas, which is a condition satisfied when Kn is n squared or n cubed or some other polynomial of degree 2 or more. So we can still have the first two parts of this theorem for polynomial sequences, as long as we assume that the transformation S is totally ergodic. And of course, another example we can use in this theorem, another example of Kn would be floor value of n squared log squared n, which technically does not satisfy the theorem of Frantzichenakis I put on the previous slide, but there is a comment in his paper after the theorem, and he can still say plenty of good things about the sequence, but I don't want to get too much into details, but you can certainly talk to me afterwards if you want to delve into those details. So that is the first of my applications. And then for the next application, I'm just going to state a special case just to make it slightly more digestible. So now we take a measure preserving system. We take a probability space and we take two measure preserving automorphisms. And once again, I assume that one of them, T, has singular spectrum. And this time I'm going to assume that S is totally ergodic right away from the beginning. Now I will take a finite collection of polynomials, integer valued polynomials. So they send the integers to the integers. I assume that the first one is degree at least 2, right? I can't apply van der Corput to linear polynomials, so I need it to be degree at least 2. And then I assume that each subsequent polynomial has degree 2 more than the previous. So this condition can be relaxed, but just to make it easy to state, I decided to put it in this form. Now we can get that this multiple ergodic average converges to the expected value. So we're taking TNF, and then we're taking the product from 1 to k of S to the pi of n times gi, where all of these f g1 up to gk are bounded functions. And the Shizaro average of this will converge to the expected value, which is the expectation of f onto the T invariant sigma algebra. And then S was already assumed to be totally ergodic. So each of these g's will just turn into the integral of g. And basically the idea here is that Host and Craw already had a paper to say that if S is totally ergodic and your polynomials pi are linearly independent, then these averages just with S and no T will converge to the expected value. So I just put some assumption to allow me to apply van der Corput to the entire collection here of these SPI GIs and deduce that this product has Lebesgue spectrum. So therefore, if this has Lebesgue spectrum and this has singular spectrum, then the average will converge to 0 and only the invariant portions will remain. So again, the general idea is to assume exactly what you need to assume to apply van der Corput, and then you have your singular spectrum sequence. Yeah, so I don't think I'll have time for the fourth application, but I'll just state this one, and then I'll state an example to show that in some of these situations, we can't extend past singular spectrum into 0 entropy. And that should be the end of my talk. So for this third example, again, I'm just stating a special case of it just to make it tangible. We take a probability space, and now I'm taking 3 transformations, T, R, and S. And I'm saying automorphism, so I'm assuming all of them are invertible, as I have been. And as always, I assume T has singular spectrum. R and S will commute with each other, but I make no assumptions about R or S commuting with T. It's only R and S with each other. And now I do have to make a rather strong assumption that S is weakly mixing, but this strong assumption is gonna give me a lot in return. Namely, I can take whatever length L I want. I take some L polynomials that send integers to integers. And this time, rather than saying that the degrees differ by 2 or something like that, I just say that the polynomials are pairwise, essentially distinct. So this means that the difference of any 2 polynomials in this family is not a constant. I'm okay with having x squared and 2x squared, but I'm not okay with having x squared and x squared plus 1. And then, of course, I need all of the polynomials to have degree at least 2, because as I've already told you, you can't apply van der Corput to a linear polynomial. So now if I take all of these transformations in polynomials, then I will again take a collection of bounded functions, and I do have to do something a little funny. I'm going to assume that one of these functions has 0 integral, because I can't actually get the expected value. I have to make this 0 so that I can make this 0. So that's a slight complication that arose here, which did not arise in the previous situation. But nonetheless, if I make this assumption, then this multiple ergodic average will converge to what we expect, because namely, if this integral is 0, we expect the average to converge to 0. And here I have a TNF, RNH, and then the product of S to the PJN of GJ. And perhaps unsurprisingly, the method of proof is the same as what we had on the previous slide, namely the assumptions of weak mixing on S and commutativity of R and S is such that we can apply van der Corput on this term, or these collection of terms, to deduce that it has the Lebesgue spectrum. And then we multiply it by a weight that has singular spectrum, and the average is going to go to 0 by the generalized van der Corput. So I think if I have the weak mixing assumption, this I hope it holds for 0 entropy. I haven't proven it, but so now I just want to give an example, because we already saw from the theorem of Farhangi that in some of these situations we can work with 0 entropy rather than just singular spectrum. And admittedly, maybe the example for my next application would be more clarifying, but I'll just stick with this one example for now. So this one example is supposed to be paired with the second and third applications that I showed you. It's not a perfect pairing, but I think it shows that the assumptions can't be vastly weakened. So our measure preserving system is just going to be the unit square with the standard Lebesgue sigma algebra and 2-dimensional Lebesgue measure. And then we take our 2 transformations to be the following. S of xy is just going to be x plus 2 alpha comma y plus x, where alpha is irrational. And then t is just going to be x comma y plus x. So we see that the system with S and the system with T, both of them have 0 entropy. Neither of these systems is weakly mixing, but the first system, the system with S, is totally ergodic. And T and S generate a 2-step nilpotent group. So even though they don't commute, they're as close to commuting as we could hope. And then the details aren't too important, but you can just pick three functions that I've written here and calculate this ergodic average. So this is a Tn f0, Sn f1, and then S to some degree 2 polynomial f2. And this average is not going to be 0. So namely, the way this ties into the previous two theorems is that this S is totally ergodic, and this polynomial, n squared minus n over 2, is degree at least 2. But the T is, the T does not have singular spectrum. The T has a Lebesgue component to the spectrum, and the S is not weak mixing. So we can see that this is not violating the third application that I showed you. Admittedly, it's not the best example because I made two weakenings, right? I weakened the weak mixing into total ergodicity and the Lebesgue spectrum, or the singular spectrum, into zero entropy. But it also shows that in the first, or I guess the second application, where we only assumed total ergodicity and not weak mixing, we again, either we can't weaken the singular spectrum into zero entropy, or we can't throw in a term with a linear polynomial. So with that, I'm a few minutes over, so I think this is a good time for me to stop. Thank you all for your attention. This applies to Hardy field functions, and it probably applies to bracket polynomials, although there might be particular values of alpha where you could have problems with your bracket polynomials.